Okay, thank you, Iman, for the nice introduction. Yeah, my name is Andrei Pavlov, and today I'm going to present an interior point differential dynamic programming method, which is a part of my thesis called Efficient Methods for Control of Dynamical Systems. Yeah, let's start. So first of all, I would like to highlight the structure of the seminar. First 5 or 10 minutes I will spend on introducing the general problem, which is a control problem, and briefly mention the previous contributions that I made together with Iman and Chris. For the rest of the talk, however, I will talk mostly about interior point differential dynamical programming. Yeah, so let's start with the control problem. Let's say we have a controllable dynamical system, and we want to establish a control technique that can guarantee performance, satisfies constraints, and can be computed in real time. A modern approach is a model predictive control technique. As advantages, I should highlight that performance is usually related to objective function, and MPC is based on minimizing the objective function, subject to a model of a dynamical system, which allows to explicitly handle the constraints and by iterative resolving, establish a closed loop control. However, disadvantages of MPC that limit its practical implementability is mostly computationally expensiveness. So we need efficient optimization algorithms to make real-time MPC possible. Also, another disadvantage is that stability and recursive feasibility analysis is usually required, and not all MPC schemes can provide such properties by design, but we will not focus on this right now. So the MPC problem, let's fix the setup. We have a dynamical system, which is given by the following difference equation. We have state and input constraints. We have stage and terminal costs. And let's say all these functions are twice continuously differentiable and nonlinear. As a research focus of my thesis, I choose solution of the finite time optimal control problem at real time. So this is the finite time optimal control problem. This is how it looks like. And the research directions which I investigated in the thesis are the following. So if we noted that the problem is parameterized in initial state X, we can try to pre-compute the solution. Let's consider a convex MPC problem as a multi-parametric program in X. And let's say we are terminal constraints, so we don't worry about stability and recursive feasibility for now. Explicit MPC techniques allows to compute the optimal control law as an affine function in X. It is actually piecewise affine function of X, with J corresponds to different regions labels. However, this approach is limited to linear quadratic MPC problems. There is another approach, which is approximate explicit MPC. Instead of computing the explicitly optimal control law, we're trying to approximate it with another control law which maintains the stability and recursive feasibility properties and might be characterized by a certain degree of suboptimality. The proposed method, which is investigated in the Minimax approximate explicit MPC, is to approximate the optimal control law with a barocentric combination of control inputs computed at different points and provide a special Minimax stability certificate for these special barocentric coordinates. As you can see, barocentric coordinates, which are given by lambda, it is actually a vector. Here are the elements of this vector. So lambda star is a solution to a small scale linear program. With this approach, we were able to make the curse of dimensionality less crucial for these kind of problems. As you can see, when the stability certificate is given by a worst case approach, it has an exponential growth even on the logarithmic scale. if we introduce anisotropic worst case, so anisotropic means that we divide the regions only in the directions where it is needed. So it's not a general approach as the worst case. It uses additional information about the problem. Then we have almost a linear growth on logarithmic scale, and anisotropic minimax allows for sublinear growth in the number of hypercubes that we need to satisfy for stability. With this method, we were able to solve a simple control problem for two-wheeled self-balancing robot. In total, it requires 24,000 hypercubes to be certified. And then linear programs are solved at 100 Hertz on a microcontroller. So it can be used at real time. We have a publication in Automatica paper. We have a video, which you cannot possibly see it because, maybe now you can see. Yeah, so here is video of the robot, which balances itself without any external information. It uses only data available from onboard sensors. It computes the control law, which allows it to stabilize and satisfy both input and state constraints. Let's go back to the slides. Let's go back to the MPC problem. So what if we don't want to pre-compute the solution and we still want to solve the finite time optimal control problem at real time using online MPC? In this case, we would like to optimize the problem complexity so we don't waste the computational efforts on solving a problem which is of excessive size or with too much accuracy in our solution. As you can see, well, let's consider an MPC problem without terminal constraints. So we have only a finite sum of stage costs. In this case, a stability is not automatically guaranteed by design, and we have to establish a prediction horizon length which is sufficiently long so the stability properties can be proved. And we have a certain degree of freedom. We have different choices for n. Also, we might consider a suboptimality in the optimization algorithms as additional degree of freedom. So let's say we want to make the problem simpler to solve, and we have an optimization algorithm. We have an estimate for algorithmic complexity. It might be worst case complexity or empirical complexity or expected complexity, whatever you want. We define the MPC complexity as the number of iterations we need to take with our optimization algorithm multiplied by per iteration complexity. Yep, and the problem will be minimize the MPC complexity subject to stability and feasibility guarantees. In the following papers, we have considered an early termination criterion based on duality gap measure and considered a so-called gamma suboptimal solution, which satisfies the gap between the current objective function and the optimal objective function is less than gamma multiplied by stage cost, where gamma belongs to the following interval. We have derived a condition which includes both n and gamma, and this condition provides a lower bound on the performance. So when alpha mean is chosen as 0, it means just marginal stability. Otherwise, it acts as performance bound. With these constraints, we were able to formulate the MPC complexity minimization problem. So the equation here comes right into the constraints, and the objective function is chosen as you wish. So to highlight one of the most one of the best results we obtained is the nonlinear MPC problem plus interior point methods. Here are the theoretical estimates for complexity with thin lines, and these are the experimental results. As you can see, it provides a nice insight on the fact that you should not choose the smallest stabilizing prediction horizon length, and you can increase it just a bit, so you can add more suboptimality in your solution. And in this way, you will decrease the computational complexity of the overall problem. Yeah, that's it for the previous contributions. And let's focus on efficient optimization algorithms. Previously, we haven't mentioned how we will solve the problem. Now it's time to develop an algorithm which allows to solve the finite time optimal control problem. Yeah, so the outline for the talk. We will start with the motivations, where we discuss why we want to compute not just an open loop trajectory as a solution, but also to provide a feedback loss. We also want to maintain dynamical feasibility, and we want to satisfy inequality constraints as it was stated right in the beginning of talk. Then the section dedicated to contribution, where we will consider a roadmap to the contribution. We will see how to solve the DDB recursion arising in our method and discuss some of the properties of the algorithm. And in the final section, we will consider practical implementation of the proposed method. We will compare the proposed method with other available algorithms and provide conclusions and outline the future work. So let's formulate the problem as we want to develop an efficient method for solving the finite time optimal control problem, stated as this. This problem is inequality constrained, so we have to use one of the techniques which allows to handle the inequality constraints. This might be sequential quadratic programming, augmented Lagrangian techniques, or interior point method. So spoiler, we will use the interior point method. We also want to get a feasible solution as soon as possible. One can use condensed problem, or one can use the dynamical differential programming method. We also want to compute the feedback laws to establish a better closed loop control properties, just like in LQR or similar to resolving the model predictive control. So the research direction would be a combination of all the aforementioned methods in the hope to combine their properties. So let's start with the last one, which is the optimal closed loop control. In model predictive control, we usually resolve the problem for each new state to get an update to our optimal control guess. However, an obvious limitation, solving from scratch is hard. And we usually need to have fast convergence for the algorithm we use to provide the real-time capabilities of overall scheme. However, there is another approach, which is Bellman optimality principle. It allows to express an optimization problem formulated in control inputs as a series of nested problems of similar structure. It has another limitation. Analytical solution is rarely available. One of the most known result is LQR, which is unconstrained linear quadratic regulator. So as a main takeaway, we would like to compute at least locally optimal control laws, not a global one, just like in LQR. Yeah, let's motivate the dynamically feasible solutions. Dynamically feasible solutions have a very nice property that it can be directly checked for suboptimality. as the constraints are satisfied, we can just put everything we have in the objective function and it will provide the current cost. However, we face an obvious issue. General purpose optimization methods satisfy the equality constraints only in the limit. So if you terminate the algorithm earlier, you might not satisfy the constraints. As a solution number one can suggest to propagate the dynamics for the obtained solution which we get from the general purpose optimization method. However, in this case, we might face a potential violation of the inequality constraint, so we have a trade-off. Solution number two is to eliminate the dynamics completely from the optimization problem by just substituting the equality constraints into the objective function and inequality constraints. So we have another problem formulated only in control inputs, x0, where x0 is the initial state and only control inputs are the decision variables. However, in this case, we face a dense hashing. So Newton's method will have a cube complexity, which is not a very good if you plan to use long prediction horizon lengths. Another solution, we can try to implement a stage-wise Newton method with linear complexity. However, it is really hard to implement, and historically it was implemented only after the differential dynamical programming method was reported in the literature. However, the original DDP method cannot handle the inequality constraints, so we will go and resolve this issue. To handle the inequality constraints, we might choose one of the three proposed methods. Well, there are actually more, but let's focus on the most popular ones. In sequential quadratic programming, we use constrained quadratic models to compute solution estimates. It is a very well established and popular method. However, it can be characterized with significant computational efforts spent for computing each solution update. So we basically resolve the constrained quadratic problem for each iteration. Penalty and augmented Lagrangian methods allows to consider an unconstrained problem instead of constrained by adding penalties either in the objective function or the Lagrangian function. So we can resolve the unconstrained problem with other well-established techniques like Newton method or gradient descent. It is sometimes useful and usually has slower convergence than SQP. So we go to the third method, which is interior point method. This method can be considered as a homotopy method, where we perturb the KKT system and resolve it iteratively for the decaying perturbation. In the end, we are hoping to convert to the optimal solution of the original problem. It is very theoretically appealing and remarkably successful in practice. So we will choose the interior point method as our workhorse. Let's present a roadmap to the optimization algorithms. So you're here, we can see the constrained finite time optimal control problem. We can formulate Lagrangian minimax problem, so we can use primal dual method. Other ways to introduce a dual problem, use dual method, or we can just use primal method. However, with the Bellman optimality principle, we can reformulate the problem and consider a nested finite time optimal control problem. The primal DDP method is the original DDP method or a combination of the original DDP method with a penalty approach when we put all the constraints into the objective function and resolve the problem in this way. So we don't keep the dual variables anymore. We can also formulate a nested Lagrangian minimax problems and use primal dual DDP method. It is in green because the contribution I'm discussing will belongs to the primal dual DDP methods. Yeah, so as you can see from the map, we have to take 3 steps to arrive to this green area. The first step is to apply the Bellman principle of optimality to the original problem. So as you can see, we have the original problem. Then we consider a nested formulation, which is minimization problems, nested minimization problems with constraints. And then we reformulate the above problem as a minimax problem. So now we have unconstrained min and constrained max problem, where S variables are the dual variables. And we have small l, which is stage-wise Lagrangian, which comes as a replacement to the stage cost. But now we have a recursion. Minimax problem to be solved requires everything inside square brackets to be either approximated or computed explicitly. And to be able to approximate it, we have to solve another minimax problem and so on. A nice thing about this recursion is that it is a finite recursion with the terminal cost in the end. So we can try to resolve the recursion from the last problem up to the first problem. And this is exactly the idea behind any DDP method. We start with an initial solution guess and then repeat the backward parse and forward parse until convergence. So the backward parse is resolving the recursion, which we introduced at the last slide, at the previous slide, from end to start, and then we update our solution from start to end. Let's answer the following questions: how we resolve this recursion, how we update the solution, and when the algorithm works as we expect. In resolving the recursion, we will rely on 3 main ingredients, which are the estimates for cost-to-go functions, denoted as capital V in red. We will consider minimax problems formulated with V function. And from these minimax problems, we're hoping to get a local behavior for the solution, so we can formulate another problem with cost-to-go function Vt instead of Vt plus 1 this time. So let's go from cost-to-go function to minimax problem. As I told you before, we have a cost-to-go function at the latest step for t equals n. So let's assume we have a trajectory which is given, and the trajectory satisfies the dynamics. It can be satisfied by propagating the given control inputs. Constraints are satisfied, and the dual variables are strictly positive. So let's consider the quadratic models of the cost-to-go functions. As the Taylor series says, we have the first 3 terms, a constant, linear term, and quadratic, plus something else. Note that the latest cost-to-go function is known and coincides with the terminal cost, which is px. So we can directly establish that the coefficients for the latest stage-to-go function are given as follows. So it's the cost, the terminal cost itself, the gradient of the terminal cost, and the Hessian of the terminal cost. So the problem at time t with this definition can be written as minimax problem of stage-wise Lagrangian function plus the v function depending on the next state computed as fxu. Let's call everything inside the square brackets q, call it q function, and consider how this minimax problem with q function can be resolved to establish the local behavior of the controls and dual variables. This is usually done by replacing the exact problem with q function with its approximation. And the approximation we use is also quadratic Taylor series. So this problem can be now resolved with respect to local changes to the to U and S, and optimization with respect to these local changes yields the following set of equations. So the first set of equations is just unconstrained minimization condition, while the second is a complementarity condition. So it's either a gradient with respect to S, delta S is 0, or the dual variable itself is 0. This is element-wise product. These equations are generally hard to solve because the last equation defines a set with no interior. So we perturb the last set of equation with a perturbation parameter mu, which is strictly positive, and drop all the second order terms arising right here. So we end up with a parametric linear system of equations. So what's special about this parametric system? As you can see, it can be already resolved for delta U and delta S as a fine function of delta X. So let's focus on the perturbation which we put inside the parametric system. Theoretical aspects of using this perturbation is to keep the solution away from feasible set boundaries. One can think of log barrier, which is an equivalent problem. It allows to make problem smoother and easier to optimize. You can think about it as being a homotopy method. However, practical aspects of using perturbation is to control the convergence by following the interior point central path, which is a set of all points defined as a solution to the system for different values of perturbation. Also, it allows to balance between optimality and algorithmic complexity. One can terminate the algorithm earlier without further decreasing a perturbation, which in general case should go to 0. Yeah, so from this system we can obtain equations which defines the local behavior of controls and dual variables. And with this local behavior defined as follows, this is exactly the fine function of delta X, which is a parametric solution of the previous system. We can establish the equations for the cost to go function model at the current time t. So as you can see, Q depends on Vt plus 1. And after we compute a solution, we can establish Vt, just Vt without t plus 1. Q hat functions are related to Q functions in a, well, in some way. Yeah, with the backward paths being resolved, one can go to the forward path. The forward path is pretty straightforward. We define the update functions. As you can see, it includes the coefficients computed for the parametric system. We denote a new solution guess with plus on top of variables. We initialize the solution at the same state and compute the update as follows. Yep, so when and why IPDDP works. We have to assume a strict primal dual feasibility. So the constraints are satisfied strictly and the dual variables are strictly positive. Matrices Q hat UU, which are related to QUU, which are QUU are the hashings of Q functions with respect to U, are positive definite. Then we can establish that the stationary points of the proposed method coincide with the perturbed KKT points. And moreover, if you are in a neighborhood of such a stationary point, you have a local quadratic convergence rate, which is really nice. Global convergence can be established with the help of line search, regularization, which is applied when QUU hat is not positive definite, and step filter. By decreasing the perturbation, we can finally converge to the locally optimal solutions under regularity and second order sufficient optimality conditions. We also get feedback control laws almost for free by just resolving the parametric system. And we can handle the primal infeasible guess after appropriate modification. So we can relax the condition C being strictly less than 0. So let's consider the modification we have to make. This is usually done by introducing flag variables. So now inequality constraints are equality constraints with new variable y, and the variable y should be positive. So these are slug variables. In this case, we have a new parametric system of a bigger size, but the condensed system, when we resolve for delta y and substitute it back to the system, looks almost the same as the previous parametric system. And finally, in the forward pass, we have to update our estimates for slug variables. So it will be 3 equations instead of 2. So let's overview the results we have so far. For the feasible IPDDP, we have to ensure primal dual feasibility. The constraints are strictly satisfied and the dual variables are strictly positive. For the infeasible modification, we have to maintain only positivity of dual variables and slug variables. For both of the methods, we have stationary points being equivalent to perturbed KKT points. And for both of the methods, we have local quadratic convergence. So in the practical implementation, where global convergence is important, we have to apply regularization, which is QUU hat plus sigma I, where sigma is a positive scalar, I is identity matrix, or any other positive definite matrix. We have to apply line search with a step size. So the update rules are now defined as follows. We have to use a step filter, which guarantees that the optimality error is strictly decaying after a step. And we have to maintain positive perturbation and reduce it in the process. Give me a second. Yep. Let's see the advantages of IPDDP demonstrated on numerical examples. So as I told you before, perturbation leads to smoothness in the problem. To demonstrate it, let's consider a very simple inverted pendulum problem with only mild nonlinearity in the dynamics. It is only sine function and constraints. So the solution to the perturbed problem are the following. As you can see, if we decrease mu, which is perturbation parameter, the solution approaches to the optimal solution, which is discontinuous bang-bang control type of trajectory. So by using perturbation sufficiently big, we can enjoy the smoothness properties of the problem. How this influences the numerical performance of different algorithms is provided in the following figure. Let's consider the first 2 methods, which the methods we propose. They have almost the same results. This is because the constraints are satisfied for the initial guess, so there is no point to use infeasible IPDDP at all. The log barrier method, which is a primal DDP method with a log barrier function in the objective function, have almost the same number of iterations, but we will discuss what's wrong with this method later. However, SQP type of DDP has a greater number of iterations before the convergence happens. It also has a greater variance. We believe that this variance is caused by computational difficulties in identifying the set of active constraints on the optimal solution, which leads to a slower progress. Yeah, so let's consider another advantage of IPDDP, which is interior point central path following abilities. So central path, as I told you before, is a set of points defined as solutions for the perturbed problem for different perturbations. And it is very important in practice to decrease perturbation only after the perturbed problem is solved to a sufficient degree of accuracy. Let's consider a car parking problem with huge nonlinearities in here. We have both arc sin function, we have sin, cos functions, and square root. And let's compare the log barrier DDP method with feasible IPDDP. We reduce perturbation as follows. So it is divided by a constant factor of k, or as a power of 1, as mu to the power of 1.2. So for the two different intervals, we resolve the problem, the perturbed problem exactly, and then reduce perturbation and try to make a step. As you can see, log barrier method cannot take the same step sizes as IPDDP can do. And in the second scenario, it almost stocks. So you cannot effectively trace the central path if you reduce the perturbation too much. By the way, in a practical implementation, we usually use k equals 5. So as you can see, it belongs somewhere here. So sometimes it can take steps, sometimes it cannot. Yep, so how it influences the numerical performance? Again, the feasible IPDDP and infeasible IPDDP have almost the same performance, while the log barrier method on this problem behaves worse in comparison to the IPDDP methods. And SQP type of DDP, again, has a larger variance. Sometimes it converges faster, maybe when it gets at the active sets right, but sometimes it doesn't. So you have to wait almost twice as more iterations to be made. Yep. And another advantage of the proposed method is its ability to handle infeasible guesses. So let's consider a unicycle motion problem subject to the following constraints. So we should not leave this area, and we want to move to the right without hitting the obstacles given by these dotted circles. As you might guess, getting an initial solution which will lead to a feasible trajectory is not a trivial task. So we have to either relax the problem or use a method which can handle infeasible guesses. So the numerical comparisons. Here we consider only infeasible IPDDP and relaxed log barrier DDP. Relaxed because we don't use a logarithmic barrier anymore. It is replaced with the following beta function. It is log barrier when the constraints are not violated, and it is this function when they are close to be violated. As you can see, the infeasible IPDDP has better numerical performance. It converges faster than the relaxed log barrier DDP by almost 20 iterations. Yeah, so finally, the conclusions. So the properties of the proposed method allows to converge to the locally suboptimal or locally optimal solutions by reducing the perturbation. It has local quadratic conversions, which is super linear in practice because we have to perform a regularization, a line search, etc. It has linear complexity in n while maintaining the dynamical feasibility of all iterates, so it can safely terminate it earlier. It has comparable or better numerical performance than all the different methods we compared with. It has modifications allowing to handle infeasible solution guesses, and it provides constrained feedback control laws as an additional output. Yeah, this can be related to the reinforcement learning where people are looking to the constrained feedback control laws from data. As a further research, we suggest trying predictor corrector steps in order to improve the quality of the news and updates. We consider an adaptive perturbation strategy as a possible way to improve the practical numerical performance. We also want to consider bi-level programs, which are the optimization problems with extra optimization problems as constraints. This method is also known as mathematical programming with equilibrium constraints. And we want to generalize the algorithm to be able to conduct optimization on manifolds. Yeah, so we have a preprint available on Archive. I've uploaded an updated version a couple of days ago. And yeah, we have a paper submitted to a journal. That's basically it for now. If you have any questions, feel free to ask me.